Chapter 10, Section 5 is all about exponential functions, and we're going to go over what an exponential function is, what it represents, what it looks like graphically, and kind of talk about some of the features that these graphs have. An exponential function would be something that shows either growth or decay. And what I mean when I say that is that it's going to show a function that increases very rapidly, or it decreases rapidly, or it could even be moving slow, but it's going to have an exponent involved, which is why it's called exponential. So over time, your numbers are going to be increasing at a constant type of rate, and it's going to just be going up or down depending on what type of function that you're dealing with. Some examples of exponential functions look like these here. All of these would be considered exponential functions because your variable is the exponent. So instead of us seeing like x plus y, or x plus 5, or x raised to the 5th power and graphing something like that, the x is what's changing as your exponent. So you're plugging in different numbers for the exponent, and you're watching how it affects the numbers that you're looking at in your chart or your graph. So when I look at an example here, and I want to graph this function y equals 3 to the x power, I am trying to figure out what my y values would be if I start putting in random numbers for x. Now, when I do these types of problems, I like to do some negative x values and some positive x values because I feel like it gives you a really good picture of what the graph is doing. Now, if you remember in the past, I've shown you guys how to use my calculators in class in typing in your function. You can still do that for these. So we did that when we were working with quadratics back in chapter 9. So if you want to grab a yellow calculator so that you can type in these functions, to use that table so that you don't have to do all the manual punching of these numbers in, and the table will just have those values for you, you are still allowed to do that. So remember, if you're doing that, you're going to press that table button. It'll give you the y equals, and you'll need to type in your function. So for this one, you would type in a 3, and then you would want to look for your caret key, so kind of that upside down V that we've talked about, and that'll get you the exponent button to show up, like on the function. And then you're going to want to type in x. Then when you go to the next menu, you can start at -2 because that's where my chart starts at here. Keep your steps still at 1, and then go ahead and get into your table, and you should start to see those values that show up. So if I raise 3 to the -2 power, you will either be given a fraction or a decimal depending on how your calculator is set up. But this would be the same thing as 1 over 9, or 1/9. 3 to the -1 would be 1 over 3. 3 to the 0 power would be 1. 3 to the first would be 3, and 3 squared would be 9. And you could keep looking at more points if you wanted to. But let's take a look at what this graph is going to look like. Now for these first couple, you may want to figure out what the decimal is in case you have a hard time understanding like fractions of numbers. But so you're going to want to see where those are at. Now you can see that they're small, so you're going to have to estimate where you think they are. They're not going to be on the x-axis because they're slightly above it there. And so when we go to graph that -2, you're just going to go barely above the x-axis and draw your first point. Same thing with that -1. You're going to want to estimate where you think that -1 or that positive 1/3 would be. Now 0 is at 1, 1 is at 3, and 2 is at 9. So you can see how over time these points start to get farther and farther apart from each other. There's a bigger difference here between 1 and 3's point and 2 and 9 than there was kind of at the start of the graph. Now, if you keep looking at points in your table, you're going to notice that anything after the 2, 9, so like at 3 and 4 and 5, those numbers start to get big really fast, okay? And that's because you're taking 3 times itself multiple times. So the number is going to be increasing rapidly. If you go the other direction, so if you start going into the more negative side of the table, you're going to see smaller and smaller and smaller fractions, but you are never going to see 0. So when you draw your graph, I don't ever want to see your lines go beneath the x-axis. It needs to stay right above the x-axis, pretty much as close as you can get it to that point without actually touching it. and then it needs to curve and follow the trend of those points there. So your exponential functions today are never going to cross that x-axis except if we move the graph a little bit. And so we'll see some examples of how you can transform these graphs. But you're just moving those points kind of in that general direction. So this is showing that exponential growth that I was talking about. Now, some information about this graph underneath it here. Domain and range. Domain would be what are like your x values. Are there any limits on the x values? So for these exponential graphs, like on my table, I could go up or down in my table for as long as I wanted to. So x is going to be able to have any real number. So I can do any negative number, any positive number, and put that in to my table and get a value to come out. Now, my range is talking about my y values. Okay, so the y is always going to be a little bit above 0. Remember I said it looks like it's approaching 0 because it's getting really close to that x-axis line, but it's never actually going to touch it. So it's always going to get smaller and smaller and smaller and smaller, but it's never going to equal 0. That's also known as like an asymptote. So if you hear me say that word asymptote, I'm talking about the line that the graph will never actually cross. So this is an exponential growth function because it has that going up shape, so it kind of looks like what we did up there above. All exponential growth looks similar to that, and that they're going up over time. So growth is going to tell you that the graph is going up and to the right. And that means that your base, so the number that you're raising to the exponent, is going to be bigger than 1. So for that example I just showed you, the base was that 3, because I was doing 3 to the first power, 3 squared, 3 to the 0 power. But my base was 3, and that's bigger than 1, which is why this was a growth function. Now if we take a look at this next one, this one has y equals 1/2 raised to the x power. So again, if you look at your calculator, you can type in this as your function in that table. And when you do this one, you'll notice that you're going to get, for numbers 4, 2, 1, 1/2, and 1/4. If you didn't notice before on that first problem, notice now that these are your reciprocals of each other. So I want you to notice the pattern of your numbers is that they are reciprocals. 4 and 1/4 are reciprocals, 2 and 1/2 are reciprocals. If I kept looking at -3, +3, -4, +4, I would see more reciprocals. But notice how these points have almost shifted in what they were doing compared to that last example. If I go to graph these ones, at -2, I'm up at 4. At -1, I'm up at 2. 0 is at 1. 1 is at 1/2. And 2 is at 1/4. And so this one is kind of doing the opposite of what that last one did, in that it's going down over time. But again, it's going to have some of the same features that the exponential growth graph had. So we can summarize that underneath our graph here. Our domain, again, is going to be your x values, which we can do any number, so all real numbers. I could continue to follow my chart, and you can see how they keep putting in different numbers for x. My range, y still needs to be greater than 0, because again, even though it's going the opposite direction, and it's going down and to the right this time, it's still never going to cross that x-axis. It's always going to be slightly above it. This is called an exponential decay function. So this means that it goes down and to the right. And that's because my base changed. On that last problem, it was 1/2 raised to the x power. So the 1/2 is your base, and that's a fraction. So if you have a fraction that's between 0 and 1, so like the 1/2 or 1/3, or it could be 2/5, it has to be a proper fraction, which means that the top number is smaller than the bottom number. That's going to be an exponential decay type function. Now we can also identify exponential behavior by looking at a table. So we don't necessarily need the graph to figure out what exponential function is being represented. So what you want to do for these types of problems is look for your pattern in your data. So look for those reciprocal patterns that I showed you on that last one, and then you should be able to go back and see them on that first example that we did. If the pattern is multiplied by a constant, that tells you that it's exponential. So it's helpful for you to be looking for powers like 2 to the x power, 3 to the x power, 4 to the x power, so on, so that you can kind of try to narrow down what your base is that's describing what's going on in your table. Okay, if the pattern adds a constant, then it's not going to be exponential, it's going to be linear instead, probably most of the time. So you want to make sure that it looks like it's following that pattern where you're just taking a number times itself and you're just changing the amount of times that you're doing that. The last option is if you can't find the pattern, graph the points, see what the graph looks like. If you can't figure out from just looking at the table, you can always try to look at a graph to see if you can notice the pattern or get an idea of what the graph is doing. Because sometimes we can look at the graph and understand like this is showing an exponential, or it's showing maybe a linear graph or a quadratic graph or a cubic or something completely different than what we're trying to find. So for example, I'm looking at this table here. My x's are going 0, 1, 2, 3, 4, and my numbers are going 1, 2, 4, 8, 16. So I'm trying to see if there's any pattern that I can find with my y's as they increase. Well, 1 times 2 is 2, 2 times 2 is 4, 4 times 2 is 8, and 8 times 2 is 16. So it looks like I'm multiplying by 2 every time. So because that's showing me this, if I think about that 2 being like my base, 2 to the 0 power, 2 to the first power, 2 squared, 2 to the third, 2 to the fourth, is going to give me all of those numbers in my table. And so my exponential function would be y equals 2 to the x power. So see if you can find the pattern for this one and what exponential function this one would be representing. So hopefully you noticed on this one that it's multiplying by 3 each time. So then if I check like 3 to the first, 3 squared, 3 to the third, 3 to the fourth, those all match what I'm getting in my y values of my table. So we would have y equals 3 to the x power as my exponential function. Now for this last example here, I really want to get into how we can start transforming our exponential functions so you can see how sometimes if you start adding, subtracting, or multiplying numbers into the original exponential function that it can actually change the way that your graph looks. And this is those cases I said that it might start to cross that x-axis because they're translating it or they're pushing the graph down or up or something like that, and so it's going to change the way that it looks a little bit. So for this one, I have my original parent function, which is y equals 2 to the x power. Again, if you want to, I would use your table function to really help you fill out all these points and then start to see what the graphs look like. So starting with the parent function, y equals 2x, we would type in that function in our calculator, or you could start thinking what's 2 to the negative 2 power, 2 to the negative 1, and so on. And so I'm going to get 1/4, 1/2, 1, 2, and 4. So this is the parent function because this is kind of where we would have started at. So down here is what we're going to do for graphing. And maybe what I'll do for right now is just help you guys fill out the chart, and then we'll look at the graph in just a minute. So the next one, you can see they changed it a little bit because they took 3 times 2 to the x power. So they put a 3 there in the front. So if I change my function and I add that 3 in there, my numbers become 3/4, 3/2, 3, 6, and 12. So you can see how my numbers got a little bit bigger this time. That's because we're multiplying by 3. So how did it change? Well, this graph is going to be stretched. That 3 is going to stretch your graph. Now if we look at -3, so instead of +3, we look at -3, my numbers are going to be very similar, except they're all going to be negatives. So you could still say that it's stretching the graph, but the really big thing here that you need to notice is that it's reflecting it, because it's going to push all those points down into the negative. So it's going to flip this graph upside down. The next one we have in our chart says 1/3 times 2 to the x power. So again, you can type that into your table function. We get 1 over 12, 1 over 6, 1 over 3, 2/3, and then 4/3. So you can see that these numbers are much smaller than what we've seen in the couple of charts before this. That's because you're taking that exponential function times 1/3. So when you multiply by a fraction like that in the front, that is going to compress your graph. It's going to cause that graph to move a lot slower than it was before because of that fraction sitting in the front. Now this next one, we have 2 to the x power, so that's like from our parent function, and then it has plus 3 added on to the end. So this one is going to be 3 1/4, 3 1/2, 4, 5, and 7. So if you look at the parent graph points compared to these, they all added 3. Like 1/4, 1/2, 1, 2, 4, all of those added 3 to get these new numbers. So because it has that plus 3 on the end, that's going to be a vertical shift. So it's going to move it up or down. If it had been subtracting, it would have moved it down. But this one is adding 3, so it's going to push your graph up 3 points. The last one here is y equals 2 to the x plus 2. So you can see how they changed the exponent on this one. So if I type in my numbers here, I get 1, 2, 4, 8, and 16. And what this did to my graph is it's going to be a horizontal shift. So it's going to move your graph left or right instead. So that's your table. Now what I want to do is graph all of these, and I'm going to use the same colors that I used for my table so you can see what graph matches with what. But this is all going to be taking this original parent function that we have, and it's going to be moving it around or changing how it looks because of all of these changes that we've made. Now, I would graph as many points as you can on your table. Mine might be a little bit more limited to the space that you guys have in your packets. But so I'm going to start with that parent function. So this would be y equals 2x. That's the parent. So that's the very original. Now the next one we said it stretched it. So that means that my graph is going to be moving a little bit faster. So it's going to increase more rapidly. So at -2, we're at 3/4. -1, we're at 3/2, which would be 1 1/2. At 0, we're at 3. So you can see how all these points are slightly above my parent function here. 1 is at 6. And then 2 is at 12. And I'm not sure I'll have room for that. It's way up there. But you can see how this one is moving a lot faster. It's starting to increase more quickly than our parent function did. Now that next one we said that it reflected it. So it's going to be your parent function with that stretch, but everything's going to be in the negative side of things. So I'm just going to graph those first couple of points, but you can see how this one, instead of going up, it's actually going to go down. It's underneath the x-axis this time, and that's because of that negative sign that was sitting in front of that 3 reflected it over. For the next one, we talked about that it was a compression, so this graph is going to move a lot slower. So compared to the red graph, it's going to take a little bit longer for it to start to shift its way up. So you can see how this one is just slowly increasing. And again, that's because they put that fraction of 1/3 in it. Okay, the next one there, the one that I wrote in blue, that has a vertical shift. So it's going to take all of your original like red points and it's going to shift them up 3 units. So that one should look pretty much the same as the red one as far as its movement goes, but it's just everything's been shifted up to the up 3 units there. And this last one is that horizontal shift. So all of these points are going to get pushed over by that factor of 2, and it's going to go 2 to the left. So at -2, you're at 1. At -1, you're at 2. So you can see how from the red one, the red graph, it went over 2 points. Over 2 points. 1 is at 8. And I don't have room to do 216 because that goes way up there. But you can see how this graph just shifted to the left there. So this gives you a really good idea, if you kind of look at the overall big picture here of our table and our graph. This really gives you a nice idea of how we can transform these exponential graphs and still do some of those same movements that we've seen in the past where you're moving things left, right, up, down, we're stretching, we're compressing, we're doing all of those different things to it.